Over the course of the next several videos, we're going to discuss financial math. So we're going to focus on interest. Interest is one of the hallmarks of pretty much every financial institution that we engage with. And so we're going to talk about different ways that interest is used and the calculations associated with those different situations. So we're going to start with the most basic situation, which involves what we call simple interest. Now this is actually the beginning of the actual finite math component of this course. So we call it Math for Business and Social Science. But if you transfer this course, you'll probably transfer it in order to cover a credit called finite math. So finite math essentially refers to the branch of math that excludes continuous concepts. In other words, things that involve infinity. So this particular class goes along one track, and then you can think of classes like calculus and then associated courses as going along a different track. So in general, the topics we're going to look at involve some sort of countability. In other words, we're looking at numbers or situations that are finite rather than infinite. So for example, we're going to focus on financial math. Typically, when we talk about financial concepts, we'll round to 2 decimal places. It's infrequent that we need more. So the idea that we have repeating, non-terminating decimals, things like that, typically we don't need to worry too much about that just because we're focusing on things that are finite rather than things that are infinite. So to start our discussion of interest, we need to get a little bit of terminology out of the way. So we're going to consider a credit-based account, which can look one of 2 ways. You can either think of withdrawing money from a lender, in other words, borrowing money, or you can think of money deposited in an interest-bearing savings account. So in one situation, we're going to talk about interest that would be accrued that you would have to pay back. And in another situation, we're going to talk about interest that's accrued that is essentially making you money. So when we're talking about an account that looks like this, the original amount that we either borrow, withdraw, or deposit in the account is what we call principal. So principal is where our account starts on day 1. We're going to use the variable capital P to represent principal. So anytime we're looking at a financial situation and you see capital P, that's representative principal. That's the amount that's in the account before we actually accrue any interest. Now the lender, that's either going to be the person you're borrowing money from, or if you think of putting your money in the bank, putting it in a savings account where you accrue interest, you are actually the lender. So in a sense, you're lending your money to the bank. So the lender is going to charge a rent to the borrower for the use of the money, for the use of this principal. And we call this rent interest. Interest is going to be represented by a capital I. So the amount of interest per account is usually calculated as a percentage called the interest rate, variable R. It's going to be a percentage of the principal that's calculated over a given period of time, which we're going to represent with the value T. So you can probably figure out why someone would charge you interest. Say for instance, you're buying a car, you can't pay for the car up front, so you're going to pay it off over time. You can probably understand why someone would charge you interest in a situation like that. But suppose you put your money in the bank and the bank pays you interest. Well, why are they paying you interest on your account? What's actually happening in order for them to justify giving you additional money? Well, essentially what's happening is the bank is using your deposit in order to finance their operations. So you might wonder, where does the bank get all the money to make loans from? It doesn't just magically appear. Well, all of the deposits that are going into the bank from bank customers, that's what the bank is using to finance all of its operations, to make loans to other customers, etc. So the bank is paying you interest because they're actually using your money in order to finance all of their day-to-day operations. So from a practical standpoint, say for instance you had $10 million in your bank account, and say you went to the bank and you said, I want to withdraw all $10 million. Well, more than likely, they're not going to be able to give you $10 million in 20s. They don't typically have all of your money there in the bank because, again, your money is spread out in different directions. So more than likely, it would take a few days before they could actually give you all of the funds for you to withdraw something like $10 million from the bank. So suffice it to say, your money is not just sitting there static in the bank. Your money is being used. The actual contents of your account are very dynamic in the sense that they're then being used in different ways. They're being used to finance other things. Okay, So different situations, either interest is money that we have to pay back, or interest is money that we're earning when we're essentially lending money to someone else. Now, what the account is worth now, think of it today. Imagine you were taking out the loan today or setting up the savings account today. What the account is worth now, before we accrue any interest, is what we call present value. So principal and present value, those are terms that represent the same thing, the same idea. Now, the total that has to be paid back in the future after interest has accrued is what we call the future value. So we can calculate up front what the future value of an account is going to be just based on knowing what the terms are for the account, what the principal is, what the interest rate is, how long we're keeping the account. That's what we're going to call the future value. You can think of that as the account balance if you were to look at the account at the end of the loan or at the end of a specific period. That particular value is going to include not only the principal, what you put into the bank, but it's also going to include whatever interest was accrued on the account. Now, all of these terms, all of this terminology is going to be consistent from situation to situation, regardless of what we're looking at, regardless of how interest is calculated. All of these terms, all of these variables are going to be pretty much the same. What's going to vary from situation to situation is the formula that we're going to use in order to do our interest calculations. So in this section, we're going to focus on simple interest and those associated formulas exclusively. So simple interest is the most basic of interest calculations. It typically results in the lowest amount of interest. In general, true simple interest is not necessarily used a lot in real life, but examples of situations where simple interest might be used. You can think of notes, which just essentially means a loan, notes and CDs that mature within 1 year. So in other words, short-term loans, you may only be charged simple interest. And then also auto loans. Many auto loans, the interest on a loan is calculated using simple interest. So all of the interest is calculated up front the day you take out a loan, and then it's amortized over the life of the loan, which essentially just means it's distributed out in a specific way. You're not paying it all up front, you're not paying it all at the very end. They calculate all the interest up front, and then they distribute it over the life of the loan so that you pay it off in just individual amounts. And then by the time the loan is paid off, you've paid off not only the principal, the original amount, the amount that was borrowed, but you've also paid off all the interest that they were going to charge you. So we're going to look at two formulas. Both of these can be used in pretty much any situation, but the one you want to use in order to be most efficient is going to depend on what you're trying to find and then also what information you're given. So your account balance, otherwise known as your future value. Think of the future value as the balance in the account at the very end, once you pay back everything or once you end the period for your investment, something like that. So the account balance, we're going to represent with the variable A. It's going to be A is equal to our principal, capital P, plus P times R times T. Now, P times R times T is actually going to be the value for our interest. So if we want to look at an account and we just want to determine not what the account is going to be worth, but how much interest are we going to be charged or how much interest are we going to make, that's going to be what we use to determine how much interest accrues on the account. It's going to be our principal times our interest rate times the amount of time we have for the investment or the loan. So if we take the original amount in the account and we add on whatever we accrue in interest, then that's going to give us the account balance for the account. Now this is going to be one version of the formula, but typically the version we're going to use is going to be this formula. It's going to be principal times the value, 1 plus R times T. And notice it's in parentheses. So that means treat all of this as one value and then multiply that entire value by the principal. These two formulas mean the same thing. Essentially what's happened to go from the first version to the second is we did what we call factoring. So you'll notice that there are two P's. There's a common P involved in these two terms. If we were to divide it out from those terms and pull it out front of everything, then this is what we would be left with. So this is just a factored version of this particular formula used to calculate our account balance. Now, a couple things that are going to be important from a practical standpoint once we start putting numbers into these formulas and once we start doing calculations. Our interest rates, in other words, the value for R, they'll typically be given as a percentage. So if you're not told otherwise, you can assume your interest rate is an annual percentage. It's the percentage applied over the course of the whole year. It's going to be given as a percentage, but it has to be expressed as a decimal in order to be able to plug it into one of these formulas. So you cannot plug in the interest rate as it is originally given. You have to convert it to a decimal in order to use it. And we'll talk about how to do that. You may be familiar with how to do that, but if you're not, we'll talk about how you would do that. And then time, T, has to be expressed in years. If it's not given in years, say it's given in months, if it's given in days, something like that, something that we can think of as a fraction of a year, then we have to convert it to years. And the way we're going to do that is we're going to take our period of time and we're going to write it as a fraction of a year. We're going to think of the part that we have versus the whole that we would need to represent the entire year. But again, we'll look at that in the context with some actual numbers, and we'll talk about what that looks like from a practical standpoint. But those are going to be two very important things to keep in mind once we start actually using the formulas. 9 times out of 10, if you don't convert your percentage to a decimal, or you don't think of your amount of time as a fraction of a year, then you'll end up with numbers that are significantly higher than they should really be if you're using these formulas and calculating these values correctly. Okay, so for the rest of the section, I just want to look at different examples, solving for different variables, looking at different situations. So make sure you have your graphing calculator handy. I'm going to show you how you plug everything like this into your graphing calculator. We're going to look at plugging in, evaluating from a couple different standpoints, particularly when we start looking at the account balance. So there's different ways to evaluate, in other words, to plug in and simplify using a formula. And I want to show you a couple different ways so you can choose and you can have a little bit more flexibility. So let's start simple. So how much simple interest will you have to pay for a 60-day loan of $500 if a 36% annual rate is charged? Okay, so what you're going to find with all of the financial problems is there's usually a lot of information given in the problem description. So where you want to start is just by identifying all of the important pieces of information and making sure you understand what values correspond to which variables. Now, a good place to start is to identify the actual question being asked. The question being asked is going to tell you what variable you're attempting to solve for. So the question here is how much simple interest? If we were to take away everything else, everything that gives us additional information, the fundamental question is how much simple interest will you have to pay? So what we're solving for is the value for interest. We call that the variable I. Now that tells me two things. Number one, it tells me what I'm solving for. But number two, it also tells me which one of the two formulas I'm going to want to use. If I'm not looking for the account balance, if I'm just looking for the amount of interest, then I want to use the formula that just involves I, that just involves the interest calculation. So in this case, for this particular problem, I'm going to use the formula I is equal to PRT. And I strongly encourage you, particularly as you're learning, as you're being exposed to these formulas and you're practicing with them, get in the habit of writing down the formula before you do anything else. Write it down with nothing plugged in, just variables, before you do anything else. One of the reasons you want to do that is because it's going to be easier to determine where you might have made a mistake if you get down to the very end and you didn't get the correct answer. You need to know what formula you were working from to start with. Also, from a more realistic standpoint, just when test time comes around and you want to show your work, having the formula written down is a great way to show part of your work. It shows someone what you were thinking of as the starting point for your problem. It shows them that you understand the structure of the problem. If you make an arithmetic error after that, okay, but at least you knew how to start the problem, you knew how the problem was structured, you knew some of the fundamental information that goes into the problem. So suffice it to say, very good habit to get into now, write down your formula before you actually start plugging in any numbers. So I've written down the formula here. This is going to be what I'm attempting to evaluate. So I'm solving for simple interest. In other words, I is going to be my variable. So I'm solving for I. I is already isolated. So what that means is all we have to do is plug in the values for P, R, and T and simplify what we get from that. And then that's going to give us the resulting value for I. Now what we need to determine is what are the values going to be for these particular variables. So principal is always going to be a monetary amount. If we're talking about American money, we're talking about dollars. So you're looking for a monetary amount. In this case, the monetary amount is $500. We're paying back a loan of $500. So $500 was the original amount borrowed. That means principal. So the original amount of the loan or the original amount of the investment, that's going to be our principal. So in this case, P is going to have a value of $500. Now the interest rate is usually the easiest thing to identify because it's going to be given as a percentage. So in this case, we have a 36% annual rate. So my rate is going to be 36%. Now, I am not going to be able to plug 36 into my formula. Remember, we have to take the percentage and we have to convert it to a decimal. So here's how you're going to do this. The word percent, if you break it into two pieces, per and cent, that actually means divide by 100. So per means divide and cent means 100. So if you take your percentage and you divide it by 100, that's going to give you the decimal version of that percentage. So if we take 36, which is our percentage, divide it by 100, that's going to give us the decimal version of our percentage, which is going to be 0.36 in this situation. So that's going to be the value we use for R. Now the other variable we're going to need is T. So we're looking for a period of time. Notice in this case it says it's a 60-day loan. Now, T is not going to be 60. If T were 60, what does that mean? If T is 60, then what we're saying is we're keeping the loan for 60 years, which is not what's going on here. We're keeping it for 60 days. You can think of 60 days as a fraction of the year. It's less than a year. So because time always has to be given annually, it has to be given in terms of the year, what we're going to do is we're going to take that particular value, which is again a portion of the year, it's a fraction of the year, and we're going to write it as an actual fraction. Now what we're going to do is the numerator is always going to be the part and the denominator is always going to be the whole in terms of whatever unit of time we're looking at. So we're looking at days. We're looking in terms of days. So 60 days is the length of the loan. What that means is that the numerator for time is always going to be 60. In this case, it's going to be 60. Now, in order to get the correct denominator, the denominator needs to represent 1 year since we're looking at a portion of 1 year. So we have to think about what 1 year looks like in terms of the particular unit of time we're interested in. So here we're talking about days. So we need to think about what does a year look like in terms of days? How many days would there be in a year? Well, in this case, there's 365 days in a year. But you'll notice I have 360 instead. This is actually a financial standard. Well, I'm trying to think of the word. It's a financial convention. That's the word I was looking for. It's a financial convention that we call the banker's rule or the banker's year. So sometimes financial institutions will take 365 days and round it off to 360. That's legal to do. That is allowed. That's not just something we're making up here to make the numbers easier. It is actually allowed. And then typically you do have to be told, are we basing it on 365 days? Are we basing it on 360 days? In this case, we're rounding off to 360. Now, unfortunately, that benefits the bank. It doesn't benefit the consumer, but it is completely legal to do and it is standard practice. So the amount of time for our loan is going to be 60 divided by 360. That's going to be the fraction of the year that this loan accrues interest over. Now you can leave it as 60 over 360 if you want. If you want to reduce it, you can do so as well. But keep in mind, everything's just going to be plugged into the formula, which means it's all going to be simplified at the very end anyway. So if you're worried about your ability to simplify this fraction, just leave it alone. Now, if you do want to simplify it, I want to show you a way you can do that in the calculator that will keep you from having to just guess and figure out what it's going to be. A fraction really is just a division. So 60 out of 360 is really just 60 divided by 360. So I'm going to actually do that division. Now notice when I do that, I get a decimal. I don't want a decimal because technically speaking, this is just an approximation of 60 out of 360. What I really want is a fractional but fully simplified version of that number. So your calculator can actually take a decimal and convert it to a fraction. If you go to the math menu, arrow frac will take your decimal and we'll convert it to a fraction. So I'm going to hit enter and it's going to take the previous line's answer and it's going to convert it to a fraction. And notice it doesn't convert it to 60 over 360, it converts it to the fully reduced form of that fraction, which is going to be 1 over 6. So again, we're plugging in numbers and we're going to simplify at the very end. So 60 over 360 is fine, 1 over 6 is fine, you use either one. 1 over 6 may be a little bit easier if you plan on maybe doing a couple things by hand, but either one is going to be fine in this situation. Now once we know all the different variable values, then we're ready to go. Now how do we know we found everything? The general rule is if you're going to solve for a variable in an equation, every other variable's value needs to be given. So you can only have one unknown value in order to solve for that value. All the other variable values must be fixed. They must be given. So in order to solve for I, we need to have values for P, R, and T. In this case, we do. We know what they are. So we can just substitute those into the formula. Now notice there's no symbols written between P, R, and T, which automatically means they're being multiplied. So $500 is our principal, times our interest rate, which is 0.36. Remember, you've got to use the decimal version. And then our amount of time, 60 days out of 360 days, which we simplified to 1/6. So now I just want to plug this into the calculator and I can do this all in one line pretty easily. So 500 times 0.36 times 1 out of 6. Now I would encourage you with the fraction, put parentheses around your fraction. That way you make sure that your calculator interprets exactly what you want it to interpret. So we're going to multiply by 1 out of 6. And then I hit enter and that's going to give me 30. Now it's going to be important to think of units here because every single one of these values has a different unit. We're talking about a monetary value, we're talking about a percentage, we're talking about a period of time. So when we're talking about interest, what are we talking about? Well, interest is an amount of money. It's the amount of money that we're being charged in order to borrow $500. So in this case, 30 is going to be $30. So we're paying back $30, that's going to be the actual charge. But if we were also asked what's going to be the total amount we pay back, in other words, what check would you have to write to pay back the loan? Well, not only are you going to pay the charge of $30, but you also have to pay back the $500 in principal. So if you were going to write one big check in order to pay off this loan, the check would be for $530. That would pay back the $500 in principal. It would pay back the $30 in interest. But here we're just looking at interest. In this case, our interest is going to be $30. Okay, let's look at another example. Now we want to find the total amount due on a loan of $800 at 9% simple interest at the end of 4 months. And then we've also been asked how much of this is interest. Okay, so let's start by identifying what we're looking at, what we're looking for. So we want to find the total amount due. In other words, the future value, the account balance, the total amount that's going to be required in order to pay back this loan, which is going to include both the principal and whatever interest we accrue. So because we're looking for the account balance in this case, rather than just interest, we're going to use the formula that involves A. And typically we're going to use the second version, the one that's factored, where we only have to plug in P that one time. So what's variable and what's fixed? Well, P, R, and T are variable. This is just a 1. This is not a variable. So it's just going to be the number 1. So because I'm looking for the amount due, this is going to be the formula I'm going to use. And again, I'm going to write the formula down. That way I know exactly where I'm starting and I know exactly what other variables I need to identify. So A is going to be our unknown, which means that we need to determine values for P, for R, and for T. Okay, so P is going to be the amount that we start with in the account. So in this case, the account starts with a value of $800. That's going to be the amount that's loaned. So that is going to be our principal. Okay, 9% is going to be our interest rate. Now remember, we can't plug in just 9 to the formula. We need to convert that to a decimal. So percent means divide by 100, and that's going to give you 0.09. You may also know a trick about converting a percentage to a decimal by moving the decimal place, which is fine. If you know how to use that, that's fine. But the issue with that is I typically notice a lot of students maybe moving it too far or not moving it far enough, and that drastically changes the problem. So doing it in the calculator, doing the actual division by 100 is going to be safer overall. It means you're less likely to, deal with human error, which is inevitable. Eventually everyone has to deal with that, myself included. Okay, so we have our principal, we have our interest rate, now we need our period of time. So it's going to be 4 months. Now again, T is not going to be 4. If T were 4, that means 4 years. We're talking about some portion of a year, something that's less than a year. So we want to write our period of time as a fraction of a year. Now here we're talking about months. So when we're relating the part to the whole, it has to be in terms of that particular unit of time. So our numerator is going to be the part, which is going to be 4, and then our denominator is going to be the whole, in other words, 1 year. But 1 year in terms of the unit of time that we're talking about, which is going to be months. So if we're looking at 1 year in terms of months, that's going to be 12 months. So our period of time is going to be 4 divided by 12. That's going to be the fraction of the year that we're looking at. And again, you can use that version of T because we're just plugging in and simplifying, or you can go ahead and reduce that and it reduces to 1/3. So I'm going to plug in all of those values, my value for P, my value for R, and then my value for T. So P is going to be $800, R is going to be 0.09, and then the reduced form of T is going to be 1/3. Now again, you can simplify this all in one line. I want to do that, and then I also want to show you another way you could simplify this that's going to be helpful in a moment when we start solving for other variables. So let's see what this would look like all in one line. Now you can pretty much type it in as given, as long as you notice those parentheses, as long as you make sure to type those parentheses. So it's going to be 800 times, notice you don't even have to put multiplication, your calculator knows you mean to multiply there. So times 1 plus 0.09. Now here we do need to put multiplication, and then we're multiplying by 1/3. And again, I like to put parentheses around the fraction, that way I know that it's grouped correctly. And then make sure you close every set of parentheses. So I have parentheses around the 1/3, and then I have to close the parentheses that I started after the 800. And so that's going to be everything we want. I can hit enter, and that's going to give me my value. Now here, what are we talking about? We're talking about the account balance, the amount we have to pay back. So that's going to be a dollar amount, $824. And then if we're asked how much of this is interest, we don't have to go back and use the interest formula. It's not really a problem where we have to use 2 formulas because the amount of interest and the account balance are very, very closely related. If you think about where the account started, $800, this is where the account ends. It ends at $824. So the difference between the two represents the interest. Any additional money that's in the account that we didn't start with didn't come from us, it came from the bank. It came as a charge, it came as the rent for this particular loan. So the way we find the amount of interest is going to be to take the account balance, the amount due, and then we subtract whatever amount represents our principal. So in this case, the difference between the two is going to be $24. So that's going to be the amount of interest. So it's always going to be the difference between the account balance and the principal. It's going to be very important to remember that once we start to look at other situations involving interest. So for simple interest, we have two formulas. We have a formula that allows us to calculate interest and a formula that allows us to calculate the account balance. When we look at other types of interest, that's not going to be the case. The only formula we're going to be given is one that allows us to calculate the account balance. So if instead we're asked how much interest is in the account, we're going to have to use that technique we just did, and we're going to have to work backwards. So always, regardless of the situation, interest is defined as the difference between where our account ends and where our account starts, regardless of any other stipulations for the problem. Okay, now I did say I want to look at how we'd evaluate this in a slightly different way. We can also do one operation at a time. And the benefit of doing one operation at a time is it forces us to think in terms of order of operations, in terms of what's really happening fundamentally as we evaluate something like this. And the other benefit of thinking about it this way is when we start solving for other variables, this is going to give us a strategy we can use to solve for other variables. So I'm going to clear this out. We know what our account balance should be $824. We should be able to arrive at that answer regardless of any technique we use, as long as that technique is correct. So I want to go back to my formula, and I want to talk about another way that we could simplify this formula. I want to think of this in terms of order of operations. So remember, order of operations gives us a particular order for simplifying an algebraic expression based on all the different operations we have represented. So parentheses, exponents, multiplication or division, just left to right, and then addition or subtraction, just left to right. So that's going to give us the order we simplify everything in. Now here we have parentheses, so we're going to start with whatever is inside parentheses. Now inside parentheses we have two operations. We have an addition and we have a multiplication. So the order of operations says that multiplication is going to take precedence over addition. So instead of typing everything in one line, I'm going to start with just the first operation based on order of operations, and I want to go one operation at a time and then just build on in order to get our actual final answer. So the first thing we want to do is take our interest rate and multiply by the period of time. So 0.09 times 1/3. Okay, and that's going to give us 0.03. So that's now in place of that multiplication. Now we need to build on another operation. So we still need to simplify fully in parentheses. So that means the next thing we need to do is we need to add a 1 to that. So plus 1, and that's now going to give us everything in parentheses. The benefit of doing this and now seeing this number is you can think of this number as the multiplier that takes your principal and increases it in order to give you your final account balance. So any principal you would take and then multiply by this value, that value is going to take your principal and it's going to generate the final balance from it. So the last thing we'd have to do, now that we have everything in parentheses simplified, is multiply by the principal. So times 800. And notice again, we get 824. Anytime you want to simplify something involving interest, without exception, the very last value, the very last operation you're going to simplify is going to be the multiplication by the principal. That's a good rule of thumb to adhere to, because once we make the formulas a little bit more complicated, doing it step by step is going to be important, but we have to make sure we do things in the correct order. This, the multiplication by the principal that's out front, will always be the very last operation that we complete when we're evaluating the formula. Okay, so the good news though, it gives us the same answer either way. Another benefit to simplifying things step by step is that's also going to allow you to show your work. So if you just plug all of this into the calculator, what if you accidentally type something wrong? Well, you're going to get a wrong answer. But no one can see what happened between you writing your formula and you getting your final answer. So it's hard to get any partial credit if you can't see anything that happened in between. You don't know really what happened, so you can't award credit for things that were good because you can't see them. So if you can simplify one or maybe two operations at a time and then write down things as you go, that's another great way to show your work, so that again you can find an error if you make an error, and so you can get partial credit for things that are good, things that do represent correct math. Okay, let's look at another one. Now I want to talk about how we would solve for other variables. Both of these formulas have a total of 4 variables. We can solve for any of those variables, and the variable we want to solve for is going to be determined by how the problem is worded. So suppose we want to earn an annual rate of 10% on our investments. What we want to know is how much to the nearest cent should we pay for a note that will be worth $5,000 in 9 months. Okay, so there's a lot of things going on here. We're talking about simple interest again. We have an interest rate of 10%, so that's an easy one to spot. That's going to be our interest rate. Okay, now time, that's also easy to spot. 9 months, so we're talking about months, so T is going to be 9 out of 12, which reduces to 3 out of 4. Since we're talking about months, we're not talking about 9 years. Now here's where it gets a little bit more complicated. The monetary amounts can represent one of 3 things. It can represent our principal, it can represent our account balance, or it can represent the interest. What it represents is going to depend on how it's identified in the problem. So what we've been told is that we want the account to be worth $5,000 in 9 months. 9 months in the future. Keywords there, in the future. We want it to be worth $5,000 in the future. So what that means is that $5,000 is going to be our future value. It's going to be what the account is worth after we take our principal and we accrue interest on it. So what we want to know, what we've been asked, is how much should we pay now in order to get something that will be worth $5,000 in the future. Another way of saying this is, what should we invest now in order to earn enough to have a total of $5,000? So because we're looking for a value now, we're looking for a value today, in order to get $5,000 in the future, our variable is going to be principal. So what we've been given is A. This is going to be A, the account balance, the future value, the amount that our account is worth in the future. And we're looking for what we need to pay now, which represents our principal. So we need the formula that's going to relate A to P, R, and T, which is going to be the formula we just used. A is equal to P times 1 plus RT. The difference here, though, is now we're plugging in different spots than we plugged into before. So with the previous 2 situations, we were plugging in for the variables that were part of the formula, and we were solving for the variable that was already isolated. Now that's not necessarily the case here. So a good place to start is just plug in what you know, and just remember, what is your variable? What are you solving for? That's going to remain variable. So A is going to have a value of $5,000. That's going to replace A. Now P is what we're solving for. So P is going to remain variable. It's still unknown. We have R is 10%. We divide that by 100. That's going to give us 0.1. So that's going to take the place of R. And then T is going to be 9/12 or 3/4 if we reduce that. So the problem here is that the variable is in the middle of the problem. It's not isolated like it was there, but we still can solve for it. What we're going to have to do now is, rather than evaluating the formula, we're really solving an equation. We're attempting to isolate this value for P. What we do is we work backwards. Based on what's happening to P, we have to undo all the things that are happening to P. We undo them on both sides of the equation, which keeps the equation in balance. And once we have P isolated, then whatever P is equal to is going to be its particular value. Now what I want you to notice is everything that's multiplied by P, all of that is constant. All of that is going to be fixed numbers. So everything in parentheses could actually be simplified because it doesn't technically relate to P. So that's a good place to start here. Anything that can be simplified, it's a good idea to simplify it. So I'm going to type in everything parentheses, and I'm just going to type it in one line. So that's going to be 1 plus 0.1 times 3/4. Okay, and that's going to be 1.075. So that is now going to be the number in parentheses. Now I'm almost there. I want to solve for P. I want to isolate P. Now notice P and 1.075, this number we just got, they're multiplied together. So what I want to do is I want to undo that multiplication. I want to get rid of it so that P will be isolated. Well, in order to undo a multiplication by 1.075, I'm going to have to divide it out on both sides. So if I were to take this particular expression and divide by that number that's being multiplied, that's going to reduce it, and that's going to leave us with P isolated, which is the goal. Whatever I do to one side, though, I have to do to the other side in order to keep the equation in balance. So once P is isolated, I'm going to have P is equal to $5,000, which is on the other side, divided by that number that I now moved over. So P is going to be $5,000 divided by 1.075, whatever that number happens to be. So I'm going to plug that into my calculator. So 5,000 divided by, now let's pause here for a moment. 1.075, I could just type that in. That would be easy to type in. What if the number I got was something that had a really long decimal and I want to avoid having to type it in again, which is something we would like to avoid ideally. We don't want to have to round, we want to use non-rounded values, and we don't want to have to type something in where we risk maybe making a mistake. Here's another option. Notice what we're doing is we're taking $5,000 and we're dividing by the number that happened to be on the previous line. Here's how we bring up the number on the previous line and we copy it into our current entry line. If you look down at the very bottom of your calculator on the negative button, right above it in blue it says ANS. That stands for answer, which means answer from the previous line. So because it's blue, we get to it using the second button, the blue button. So if you were to press second and then negative, it's going to enter ANS, which again just means the answer from the previous line. So what we're now doing is we're taking $5,000 and we're dividing by 1.075, but we're dividing by it based on the fact that it was the answer from the previous line. That's going to keep us from having to retype anything or from doing any actual copy and paste operation. And so I'm going to hit enter, and that's going to be the value I want. Now, please pay attention to the rounding directions. A lot of people feel like they're not doing the problems right, they're getting the answers wrong, but they're really doing it right. They're just not paying attention to the rounding directions. Make sure you always look for those directions. Particularly when you're doing your homework, you will be given rounding directions every time. Make sure you follow those directions. So we want to know what's going to be the value to the nearest cent. In other words, 2 decimal places. So 2 places, that's going to be 0.16. The number after the 6 is a 2, which means we're going to leave it as is. We're just going to leave it as 0.16. So our value is going to be $4,651.16. We know it's monetary because we're solving for principal, and we just discussed the rounding. Now here's a way to make sure that your answer makes sense. Principal should always be smaller than your account balance. The idea is that interest grows your account. Either it grows your investment or it means you have to pay back more in terms of a loan. So if you're given a value for A and you're solving for a value of P, the value you get for P should always be less than A. If it's not less than A, then that's a red flag that something went wrong. Maybe you mistyped something into your calculator, maybe you didn't plug in values correctly, but that's your indication that you need to go back and check things and see what might have gone wrong, because P should always be a smaller value than A. Okay, let's look at solving for another variable. So our formula involving A actually has 4 variables. We have A, we have P, we have R, we have T. So we just looked at how we'd solve for P. Now I want to talk about how we would solve for R and how we would solve for T. We also need to make sure we can identify situations where these would be the variables we want to solve for. So let's look at another example. So Treasury bills, also known as T-bills, are one of the instruments that the U.S. Treasury Department uses to finance the public debt. If you buy a 180-day T-bill with a maturity value of $10,000 for $9,893.78, What we want to know is, what is the annual simple interest rate that you are earning? And we want to write it as a percentage, correct to 3 decimal places. Well, clearly identifying the question, it says, what annual simple interest rate? That's the question. So automatically that's an indication that R is going to be our unknown. That's what we're solving for. Now, if R is our unknown, it means all of the other values we would have need to be given. All of the other variables, we need to have an actual value for those. So time should be given. That's usually another one that's fairly easy to identify. So we've been told that it's a 180-day investment. So time is going to be that fraction of a year, so 180, and it can either be out of 365 or it can be out of 360, just depending on the situation. Here we're going to take it out of 360, and the benefit of doing that is 180 out of 360 actually reduces nicely. It just reduces to 1/2. So that's going to simplify the mathematics at that point. Now, what becomes difficult is identifying what the other numbers are, because we're now looking at 2 different monetary values. Which one is the account balance? Which one is principal? Or are we looking at a value that represents interest? The key words here are maturity value. Maturity value means the same thing as future value. When we say that an account matures, it means that essentially it's wrapped up. It's added in all the interest that should be accrued. It's matured. So the maturity value is $10,000. That means that's going to be our value for A. That's what the account is going to be worth in the future, specifically after 180 days. Now, it said that we bought this particular investment that's going to be worth $10,000, and this is how much we paid for it. So this is actually going to be the principal. Remember, principal is always going to be smaller than the account balance, than the future value. So the general idea here is we essentially invested this much money, and by the time the loan ended, by the time the investment ended, this is how much we had as a result. This was the total value of the account. So this is the value that the account started with, and this is the value of the account once the investment ended. So this is going to be our value for principal. Now, because we're talking about maturity value, it doesn't say anything about interest. It's talking about the account balance. That's our indication that we're using the formula involving A. So A is equal to P times 1 plus RT, using that same formula again. So let's plug in what we know, and then we'll leave variable what we don't know. So A is going to be $10,000. P is going to be that particular value. Now, R is still unknown, so we're going to leave that as a variable. Remember, this is just a 1, it's not a variable. And then T is going to be 1/2, so R times 1/2. Okay, now this is significantly more complicated of a situation than the one we encountered before. Now our variable is even further inside the formula. So this is where identifying one operation, evaluating one operation at a time will become helpful. It helps us get in the mindset of order of operations. So I want to forget about the other side of the equation for a minute. I just want to look at what I have on the right-hand side of the equation. And I want to think in terms of order of operations, specifically operations applied to the variable R. So what I want to determine is, if I think about starting with the variable R, what operations are applied to R and what order are they applied in? Well, order of operations tells us, of course, we start in parentheses, which is where R is. And if we were to take R and then apply one operation at a time to this value, first thing we would do is multiply by 1/2, okay? The next thing we would do would be to add a 1. And then the very last thing we would do would be to multiply by the value out front, which represents our principal. So we would multiply, we would add, and then we would multiply by the number outside of parentheses. Now, why does this matter? We don't actually have a value for R, so we can't actually do any of that. It matters because that's going to tell us the order we have to do things in order to get R by itself, in order to solve for it, in order to isolate it. What we're going to do is we're going to work backwards. So if this is the first, this is the second, and this is the third operation, we have to get rid of the operations in the opposite order. So we'll start with the last thing that will be applied, and that will be the first thing that we have to undo. So we're reversing all the operations, but we're reversing them in the opposite order. So this particular value was multiplied. There was a multiplication. So in order to undo it, we have to divide it. So I'm going to take that particular value, and in order to reduce it, get rid of it on this side, I'm going to divide it on both sides of the equation. And what that's then going to leave me with is everything that was in parentheses, which is 1 plus r times 1/2. So notice we've now eliminated one of the operations that was being applied to r. Now we also have to simplify everything on the other side of the equation. So what is that going to look like? So we're going to do 10,000, and we're dividing by $9,893.78. Okay, now you get a nasty decimal here. That's the first time we've encountered one of these. If you're going to show your work and write things down, you can abbreviate this. But you want to keep this in your calculator. You do not want to clear this, because what we're going to continue to do is we're going to build off of this. This is sort of an intermediate answer. We're going to build off of this, and every time we build off of it, we get closer and closer and closer to the actual answer to the problem. So I've written down an approximation of it over here. If we want to round to 3 decimal places at the end, I kept 6 here, which should hopefully be enough. But we're not actually going to round, because we're just going to keep building on the numbers we have in the calculator. So now that everything is simplified as far as it can be, we want to look again at the side containing r, and we want to see what else we can do. So the last things remaining are the multiplication and the addition in that particular order. So if we were to apply operations to r, we would multiply and then we would add a 1. That means if we want to isolate r, again, we're going to work backwards. So if the final operation here would be the addition of 1, that's going to be what I have to undo next. So it was an added 1, which means I'm now going to subtract it. I have to subtract that number from both sides. So I'm going to subtract it on the right in order to eliminate it, which is going to leave me with this. But in order to keep everything in balance, I have to subtract it on the other side as well. I'm going to keep that running in the calculator. So from that last number we got, I'm going to subtract 1 in order to balance the equation. And again, in order to show work, I'm just going to write down an approximation, but I'm going to keep that running total going. So now the only thing we have left is that multiplication by 1/2. Now you can get rid of this one of 2 ways. Technically it's a multiplication and you want to divide it out, but dividing by a fraction means we then have to execute another procedure. So another way to think of this is think of multiplying by 1/2 as being the same thing as dividing by 2. It means the same thing. We're cutting something in half, which is the same thing as dividing it by 2. So we can multiply by 2 in order to get rid of what we can think of as a division by 2. And what that's going to do is the 2, which we can think of as being part of the numerator, is going to cancel. It's going to reduce that 2 in the denominator, which just leaves us with a 1 that doesn't really mean anything. We don't actually see the 1 at that point. Now again, I have to do the same thing on both sides of the equation. So if I multiply by 2 over here in order to isolate my r, I have to also multiply by 2 on the other side in order to keep my equation in balance. So I'm going to take my most recent answer and then I'm going to multiply it by 2. And once we do that, notice that isolates our r. So what we're left with is now going to be our final answer. Now, it's almost our final answer, but not quite. It's the version of the final answer we would have in order to work with this number algebraically. But remember what we were solving for. We were solving for an interest rate. So this is an interest rate, but it's the decimal version. It's the version that we would plug into the formula. So it's not the actual percentage. Remember, if we started with a percentage and we wanted a decimal, we divide by 100. So if we want to go backwards, we would then take the decimal and we would multiply by 100. We would undo a division by 100 by reversing it and multiplying by 100. So if I multiply by 100, that is going to give me the percentage. So when it says round to 3 decimal places, it doesn't mean round this answer to 3 decimal places. It means once it's converted to a percentage, then you want 3 decimal places. So in this case, we're going to have 2.147, and that is going to be our percentage. Now, how could we verify that this does in fact work, that this is in fact the correct answer? Well, if you were to, again, think of it in terms of the decimal version, if you imagine plugging it back in place of r and then simplifying everything in the formula, we should be able to get to the value of a that we were supposed to. So anytime you're solving an equation, you can always go back and plug in your answer. Make sure that once you plug it in, both sides of the equation are balanced. Now keep in mind, if you plug in this value converted to a decimal, you will not get complete balance. Why is that? You won't actually get a 10,000. It won't be equal to 10,000. That's because this is rounded. So everything done in the calculator was not rounded, but as we got to the final answer, we did have to round. So you have to keep in mind that plugging things back in and simplifying, the actual answer you get when you do that is dependent on how much you round it. But as long as it's really close, which it will be, that's an indication that more than likely your answer is correct and it does make sense. So that's what it's going to look like when we solve for r. Now the only other value in this case that we can solve for is going to be t, and it's going to look virtually the same because r and t, basically the same thing is happening inside of our formula. So one last problem. How long will it take for an investment of $400 to reach a balance of $500 if it accrues simple interest at a rate of 10%? Okay, so interest rate, that one's easy to spot, 10%. So our rate is 10%. We convert it to a decimal, which is 0.1. Now the other two values we have in here are monetary, and the question was how long will it take? That's a question involving time, so that means time is our unknown. So how long will it take for an investment of 400 to reach a balance of 500? So we're starting with 400 and we want to have a future value, an ending balance of 500. So that means our principal is going to be 400 and our account balance is going to be 500. As always, principal should be smaller than the account balance. Always, they will be related that particular way. So in this case, saying that P is 400, saying that A is 500 makes complete sense. So because we have the account balance and the principal relating those values, again, we're going to use the value, we're going to use the formula with A. So plug in, A is 500, P is 400, we have 1 plus R, which is 0.1, and then T is our unknown. Now again, T is inside this formula. We need to isolate it, and whatever we get T is equal to, based on isolating it, that will be the value for T. So I need to work with my way backwards. Again, I want to go through order of operations in order to analyze what needs to happen and what's the order in which these things need to happen. So if I were to think of the operations that are applied to T in the order in which they're applied, first thing we would do is multiply by 0.1. Okay, so that would take care of that. Then we would add on 1, which takes care of everything in parentheses. And then the last thing we would do would be to multiply by our principal, $400. So that means if we want to isolate our T, we have to do all of those reverse operations in the opposite order. So we have to get rid of everything, but we have to get rid of it in the opposite order. So if the final operation applied to T was the multiplication by 400, that will be the first operation that I eliminate when I'm solving for T. So 400 was multiplied. That means I have to divide it out in order to eliminate it. But I balance it by doing the same thing on the other side of the equation, which is going to give us 500 divided by 400. So let's simplify that. So 500 divided by 400 is going to give us 1.25. And notice that's not rounded. That's an exact value. These numbers are a little bit better than the ones above. Okay, so that's been taken care of. Now we're still multiplying by 0.1 and we're still adding a 1 in that order. So that means we need to undo the operations in the opposite order. That means the 1 needs to go away first. So it was added, which means we have to subtract it to move it over. So if we subtract a 1 on the right, that just eliminates this term. Then we also have to subtract it on the left. So again, we've got that preliminary total, just subtract 1 directly from that, and that's going to give us 0.25 on the other side. And then the last thing applied to t is the multiplication by the decimal version of our interest rate. It's multiplied. So if we want to get rid of it, move it over, we have to divide it. So we're dividing both sides by 0.1 in order to eliminate that. So divided by 0.1. Now before I hit enter, I want to talk about what's going to happen here. It's going to seem a little bit strange what happens. Normally when you divide, your answer gets smaller, right? You take an answer, you divide, you get something that's smaller. In this case, when I hit enter, the answer is going to get larger. In other words, it's going to take something like 0.25, and the result of dividing here is going to give us a number that's bigger than 0.25. Why is that? Well, when we divide by something that's less than 1, something fractional that's less than 1, that's the same thing as multiplying by a number that's greater than 1. So what this really means right here, this is really 1/10. We could think of that as the fraction version. Dividing by 1/10 is the same thing as multiplying by 10. Those operations are the same. They sound different because it's different operations. Multiplication and division are different operations, but the result of doing those two things is equivalent. So it might seem strange when we get an answer of 2.5 when our answer got larger, but again, that's because we were dividing by something that was less than 1, which then increases the answer. It increases the output we get. So that is going to be our final answer. That was the last operation to undo, and so we're left with a value of 2.5. Now again, we need to pay attention to units. 2.5 what? Well, t was our variable. T is always given in years. We've seen a lot of fractional t's before. Now we have something that is bigger than 1. It's bigger than just a part of a year. So 2.5 in this case is going to be an annual amount. It's going to be the number of years. So after 2.5 years, we'll go from $400 to $500. Now, this is actually a fairly easy one to plug back in and check. So just to show you what that would look like, what do we actually want to do? Well, we have a value for P, a value for R, and now we have a proposed value for T. If I were to plug in all of those values to the formula, I want to verify that those values are then going to give me an output of $500. In other words, I want to verify that all of these values coexist in the context of this particular formula. They actually satisfy the formula and make it true. So a way I could check my answer is to take this, plug it in for T, and then plug in the associated values of P and R. So P was 400, so I'm going to plug that in. So 400 times 1 plus R, which is 0.1, times T, which is 2.5. That would be what I have on the right-hand side of my equation if I were to plug in P, R, and T. And what I expect when I hit enter, if I've done everything right, and if this answer is correct, I expect that I'll get an output of 500. And sure enough, I hit enter, I get an output of 500. So that verifies that this T is the correct value in association with these 3 other values associated with this formula. So we've actually looked at solving for all the different variables. We've solved for interest 2 different ways using the formula and then working backwards if we have the account balance. We've looked at how you'd solve for principal. We've looked at how you solve for your interest rate, and then also how you would solve for your value for time. So the next couple videos, we're going to build on this idea. All of the terminology is essentially the same. Interest means the same thing. Principal means the same thing. The account balance means take principal, add on your interest. What's going to change is how we calculate interest. So more than likely, you've encountered a situation where your interest is compounded. We're going to talk about what that means in the next video.